Good morning, everyone. So another talk of my our work. But again, I would like to do it as a teaching talk. So because even though I will show you some results, so where we applied these techniques, I would like to introduce this technique. Since if you study non-autonomous systems, then this is a very useful tool to work with snapshot attractors. And therefore, I would like to introduce this here to tell you how one can tackle these type of systems. As I already mentioned in previous talks, is that for non-autonomous dynamics, we have still to develop the mathematics. So the mathematics for non-autonomous systems with arbitrary time dependence in terms of nonlinear dynamics is not known. And so this is just now, still it's in its infancy. So it's developing very rapidly, but still, so to say, there is a lot to explore and a lot of methods have to be developed. So because what we are used to in nonlinear dynamics is that we have attractors, we have saddles, so we know stability notions and all these kind of things. And when you go to an arbitrary time dependence, and the emphasis here is on arbitrary, because for periodically forced systems, you can always transfer everything into a Poincare map. And then, of course, you are in the world of maps. And then you're again fine in nonlinear dynamics because you have all this machinery which has been developed over decades at hand. But as soon as an arbitrary time dependence comes into play, so then new definitions are necessary. What is an attractor? What is a saddle? So how can we understand these things? And so this is what I'm going to talk about. And so now this is not advancing. Yeah, it is. No, I think, yeah. As we discussed during the last days already, so we are interested in developing mathematics, particularly for climate change. So that means we would like to study the impact of climate change on certain systems. In our case, it's mainly ecological systems, but of course, all this machinery you can apply in other contexts as well. And so we have already discussed the timescale issue, so that we have different timescales we have to deal with, and you have drivers which change with a certain speed. Today, I would like to show you results for highly multi-stable systems. So because this is what we have not addressed, so we had already learned from Manish's talk what is multi-stability, so that we have basins of attraction, which we have to take into account. And today I would like to address exactly this question. What happens if we have climate change acting on a multi-stable system? So that means you have lots of different attractors coexisting. Each of them has a basin of attraction. Often they have even very complex structures. So these are fractal basins of attraction, what you can expect in a highly multi-stable system. And you have all the time permanent and transient chaos. So, and this has not been addressed before. So what happens when we have now a parameter changing? What happens to the permanent and the transient chaos in this case? So what do we have to expect as a dynamics when we have lots of different attractors coexisting? So in the literature, as I mentioned already several times, most of the time people think in bifurcation diagrams. So they think there is a bifurcation diagram and you traverse in a way the bifurcation diagram. You are sweeping your parameter through the bifurcation diagram and you go from one solution to another. This is true as long as your sweeping is very slow, so that it is a kind of quasi-stationary approach. If this is not the case, then we will see something else can happen. And this is what we would like to discuss here. Now, so as we already know, and I would like to remind you, so we had this kind of pictures here already several times. So the slow trend would be traversing the bifurcation diagram, but here we see new rate-dependent phenomena when our trend is fast and our parameter changes fast. And I remind you, we have two timescales, the timescale of the driver and the timescale, the internal timescale or intrinsic timescale of the dynamical system. And so this is the dissipative timescale. Usually this is 1 over the eigenvalue. If you have a fixed point, for instance, the real part of the eigenvalue, so that you get this kind of timescale. So this is the dissipative timescale. And now we would like to study a system. Okay, so let me start with some scientific background, so to say, to understand how we can study this kind of questions. Because, as I said, so the notion of an attractor, and when we talk about a multi-stable system, then we have lots of attractors, is, so it's not well defined in a non-autonomous context. There are, of course, now, so to say, definitions, and I would like to show you 2 of them here. And they go back, in principle, already to another discipline, to random dynamical systems, because the idea stems from random dynamical systems, and we would like to look at the Lorentz model, so which probably everyone who has ever touched chaotic dynamics is familiar with the Lorentz model, because this is one of the paradigms, and we have seen it already here in the talks. So this is just an approximation of the atmosphere. So this is the very simplified model of the convection rolls which arise in the atmosphere. And so this is, so to say, the simplification which comes up by a mode, so to say, a mode approach solving partial differential equations in original. So this is the model, and this is the chaotic attractor which pops up there. And when people study this in terms of the impact of noise, there are 2 possibilities what you can do. One of the possibilities is that you take, so to say, different realizations of your noise process, you apply it to your dynamical system, and then you look what the trajectory is doing. But there is also a completely different approach, which is called random dynamical systems, where you do the following. So you also take this system of equations here. This is, again, the Lorentz system, which we saw previously. And then you add the noise terms, which is here a multiplicative noise, as you see. And then instead of having a bunch of noise realizations which you are studying, you do the following. So you take different initial conditions and you take the same noise realization for each of them. So this is a completely different approach in terms of thinking. So because now you look at each trajectory, so to say, so which can happen in this system deterministically under the same noise impact. And this gives you such a picture. So you have an ensemble of trajectories. Here it's 1.5 million, if I remember correctly, so to produce these wonderful pictures. And what you see, they have all the same noise realization. And instead of what you usually get, the blurring of the attractor, you see the wonderful fractal structures, but you see them, so to say, developing in time, because the noise realization, so to say, goes with the deterministic dynamics, and every trajectory gets the same noise. And then you preserve, so to say, these wonderful fractal structures, and see still, so to say, the dynamics and the geometry, so which is hidden in this random dynamical system. So these are different time instants now, because now you see the trajectory evolving with the whole bunch of noisy trajectories, and each is plotted. So the state of each trajectory is plotted at the same time instant. And the color coding here reflects how many trajectories are in the same area here, so to visualize the geometric properties. And this idea can be transferred. So this idea, which comes originally from stochastic dynamics, so that you look at random dynamical systems, you can transfer into into an approach for non-autonomous systems. Because there you can pursue, so to say, the same approach. You take now an ensemble of trajectories again. So this is an ensemble approach. And each of these ensemble members experience the same dynamics. So you are initializing your trajectories far in the past, and then evolve each of these trajectories under the driving, under the non-autonomous driving, and then so you see that it's evolved with the same equations. So this yields also an attractor, because when you look at this, so there are different trajectories in the past. The blue ones are not so far away in the past as the red ones. So you go, in principle, in mathematical sense, you go to minus infinity. Of course, numerically, you don't do that. But you go very far in the past. And then you see all the trajectories converge to the same thing. And this same thing is an attractor, because it attracts all the trajectories from the past, but it is called a pullback attractor, because you have to pull your trajectories very far into the remote past to see the attractor. And this attractor, because the driving is deterministic and has an arbitrary time dependence, moves in state space. So this is not something what we are used to have in an autonomous system, that this is an object which is in state space, which is only characterized by geometrical properties. Now it has also dynamical properties, because it's moving in state space all the time, arbitrarily. And this is shown here. So all these trajectories are converging. They are converging to this pullback attractor, and this moves in state space. And so this last part here, so to say, is the attractor. This is the pullback attractor. So this is the transients, as we know from autonomous dynamics, but this would be attractor. And so we can also have periodic ones. So this would be a periodic pullback attractor. So it looks like this kind of object here, and this kind of object here. So these are the attractors which are, so to say, moving through state space in time. So this would be the time axis here, and then so the whole object, the periodic solution, is moving in state space with this time evolution. And this is what we can do in, so to say, non-autonomous dynamics. In parallel, there was another concept which has been developed in physics. And while this was, so to say, in mathematics, the pullback attractors coming from random dynamical systems. So in physics, it has been developed in the 90s, and it was called snapshot attractors. And in principle, it's the same, but it's a lot easier to compute. So because what you do is the same thing in principle, instead of trying to look at different, so in random dynamical systems or in stochastic systems, so you would have also, again, the idea of different realizations of the noise, then you get these blurred objects. But if you take an ensemble of trajectories, you see this, and this is a map, under the same, for different initial conditions, under the same noise realization. And this concept, you can again, so to say, of snapshot attractors, is in principle the same as the pullback attractor. The pullback attractor is a whole object which includes the whole time evolution. A snapshot attractor is just a slice of it. It's just so you look at some time instant, you look how the trajectory or how the attractor looks like. This is what you get. It would be like a sausage. The sausage is basically the pullback attractor, and a slice of this sausage would be the snapshot attractor. And this is very easy to compute because this is very helpful. You can very easily compute it because you just take an ensemble approach, you take an ensemble of initial conditions, and you evolve them forward under your non-autonomous driving. And therefore, this is for physicists and in applications, so this is the good thing, what you can do. So this would be a chaotic snapshot attractor. You see it here as a Poincaré section. This is also a Lorentz system, but not the one from 1963, but 84. It's also an atmospheric model, a simulated one, with now a time-dependent driving here, so which is sinusoidal. So therefore, we can work with the Poincaré section to see the attractors. And this would be basically the time evolution here of this chaotic thing. And you see, so this attractor has a wonderful fractal shape still. So you see still all the geometric properties, and you see the time evolution in state space. And this is, so to say, the advantage of this method. And you can even do it in experiment. This is an experimental thing. So it's an experimental realization of a visualization of the chaotic motion in a fluid. So you just sprinkle initial conditions in terms of floaters into your fluid, and then you watch their movement in the fluid, and then you see these kind of structures. So the visualization of chaotic structures, so which are present in flows, so what is called chaotic advection, for instance. So you would use these type of methods also to visualize these fractal structures in a flow. So therefore, it has a very applicational point of view, and so therefore, it's easier to understand. Is there a question? Yes. In the flow, so these are Hamiltonian systems, but they are time dependent. So these are in the flows, it's a time dependent Hamiltonian system. For the other attractors, which I have shown, these are dissipative systems. So these are dissipative systems. You can visualize, so to say, the chaotic advection term, because the particles which are advected so are the visualization of the chaotic structures, but they are embedded practically in a time-dependent Hamiltonian flow. So now let's see how this concept of snapshot attractors can be used to study non-autonomous dynamics. So we will now look at an example, and it's a simple example because it's nothing else than a pendulum with a periodically forced suspension, which is moving periodically here back and forth. It has a certain amplitude of the driver here, and there is a dissipation here. And so this is basically determining the dissipative timescale in this system. And now we have here, so to say, the idea, let's put on this dynamics, which has been studied in the past quite a bit. So we know the bifurcation diagram, so all the dynamics is known in this system. So for the case where we have just a periodic forcing, so then all what we know from nonlinear dynamics can be applied. Everything is fine. Bifurcation diagrams are well explored. But now we take this kind of forcing amplitude, which is here, which is a parameter in the autonomous case. So we make it time dependent. And our time dependence should be exponential, so we switch it off, and we do it exponentially. So that means we start first, so to say, getting onto some attractor, which is known in the autonomous case, and then we start switching off the thing. And this rate, and therefore it's done exponentially here. So because also the dissipation, which brings you to the attractor, is also exponential. So therefore, so that we have a direct comparison, so therefore it's an exponential switch off. So when we switch off this driver here, so we know already what is the final state. The pendulum is at rest. Nothing else can happen if there is no forcing anymore. So there will be a pendulum at rest. So this is what we have to expect. And now we change our driving. And so this would be the dissipative timescale here. So this is basically the same, and if we would switch off our driver, so with the same rate as the dissipation, so we will take one rate, so to examine the dynamics, which is a little bit slower, and one which is a little bit faster. But they are comparable. This is important. So that we are not in a quasi-stationary approach. Now, wait. Now let's have a look at individual trajectories. Okay. So let's have a look at an individual trajectory. As I said, the pendulum goes at rest. So we see here the angular velocity and the position, so which is between minus pi and pi, and this would be angular velocity. So we see that there is a rotation here, and then, so to say, it goes to the rest state with one trajectory. Now we take another trajectory, which is slightly different. So you see the difference is not that much. And we see the dynamics completely different. So it's better visible in the velocities, because here we have a counterclockwise rotation, we have a clockwise rotation, and it's first counterclockwise, and then it's jumping to a clockwise rotation. And then, so to say, it goes to the rest. So that means we have a very sensitive dependence on initial conditions. And so how it goes to zero. And therefore, this is already a hint, so that a single trajectory doesn't help much. So we have to go to an ensemble. And so when we compute an attractor, we can also do it in different ways. So we can either take a very, very long trajectory and plot the Poincare section, because it's a periodically forced system, and then we end up with an extended chaotic attractor. So if this is now a frozen in driving, that means it's frozen to one parameter value. And we can also compute this attractor in a different way. We take a bunch of initial conditions, an ensemble, integrate them all forward, and plot them all together at the last time instant of our integration. This gives you exactly the same result. So this is again a snapshot attractor. So what we then see, and so we will start now our switching off of the driving on this attractor. So this is a fractal object in state space, and we then look how the ensemble of trajectories will evolve. So we will see all the time now on the left, so what is the value of our driving? So we are now here. We start here, basically. We have seen our chaotic attractor, which develops here. So all our initial conditions have now reached the attractor. Now we start the switching off with the two different rates here. And to the right, we see for the different rates, what is the snapshot attractor. So we switch off now the driving, and it goes further and further and further and further. And what we see is we are almost at zero with the driving. But so what we see is still a lot of dynamics. Here's a huge variability. So here the dynamics is still chaotic. Here is, so our pendulum is swinging now. So, but so what we see when the scenario is fast, so when our rate of change of the driver is basically fast, we see still a lot of chaos, while here it's not. And now we can have a look, so to say, what we see, so and compare it with our bifurcation diagram. So here's the bifurcation diagram, which is known for a very long time. So we started here and go through the bifurcation diagram from here to here. So when we are here, so this was the first picture I showed, so then we should expect two periodic solutions, and they are here with these two dots, but what we see is something completely different. So because we see still a remnant of our chaotic set somehow, but so it does not correspond to what is shown in the bifurcation diagram. To come here, so this was the next value I showed. We have three different periodic solutions. Again, we don't see it reflected in what the bifurcation diagram shows in the dynamics what the snapshot attractor in the real non-autonomous case is showing to us. And the question is, what do we see instead? So, because what we see is a chaotic motion, and it has nothing to do with the periodic solutions we have to expect from the bifurcation diagram. So there is not such a thing that we are traversing the bifurcation diagram. Something completely different is happening. And now I remind you so that for multi-stable systems, often the base and boundaries are fractal. So this is the case here. So when we compute for this parameter value in the frozen in case, so there's no change in time for the driving. So then we can compute the basins of attraction. This is it. So we have here the two periodic solutions and the two basins of attraction, and they are fractal. And embedded in these fractal boundaries are usually chaotic saddles. So chaotic saddles are, so to say, present here. And they are of saddle character, so therefore they are unstable, but they are present in state space. And now the hypothesis is, this is what we see. So we see the saddle, and we don't see, so to say, what the attractors are. And let's check these ideas. So then transient chaos is something which is well known already for a very long time. So it's basically the unstable counterpart of a chaotic attractor. It's unstable. So any trajectory will leave this object, and it leaves it, so to say, with a certain rate. So there is a so-called escape rate, which characterizes the chaotic saddle. So this would be the chaotic saddle for the same value of the, so again, computed in the autonomous case, because this is where you can compute it. For the non-autonomous case, you cannot compute it, but this is the one. And now we try to figure out whether this object has anything to do with what we finally see in the non-autonomous dynamics. To do so, we have still to go one step forward, because as any saddle, like a saddle point, a saddle periodic orbit, so this object has stable and unstable manifolds, and one can compute them in an autonomous case. This would be the stable manifold, this is the unstable manifold, and their intersection gives you the chaotic saddle, which is this one. So this is the construction of this kind of chaotic saddle here. So when you overlay these two pictures, you get the intersection points. If you plot them, then you get the chaotic saddle. So, and when the trajectories leave the chaotic saddle, then they leave it along the unstable manifold, and this is this thing. And therefore, we now compare our trajectories with this object, because this is the object, so which should have similarities. So this is shown again here. So this is for this parameter value, which we have seen several times. This is the chaotic saddle. This is its unstable manifold, or filamentation, it's also called when it's a chaotic thing. And then we overlay it now, so with our dynamics, which is in red, and the black thing is this one here. And we see they are quite similar. Of course, they cannot be exactly the same, but it gives us, so to say, an indication that what we see is something like this chaotic saddle, which evolves in time. So because it has to evolve in time, since we are driving the system, and what we see in red here is the time evolution of this chaotic set, and it reminds very much to this chaotic saddle. Wait, we can, yeah, okay. And that means this is what we see. And when we plot the bifurcation diagram with all the transients, so then you see all what is gray, so there is the chaotic saddle present. And that means in all this region, this explains now why we see, when we go from here to here, we follow basically the chaotic saddle and not the attractors. So the chaotic saddle basically becomes the attractor in the non-autonomous case. Of course, we cannot prove this, But so this is the conjecture from all the numerics, what we can see. And there is no bifurcation tipping here. We don't see any, so to say, relationship to what the bifurcation diagram is telling us. And that means the dynamics in the non-autonomous case is completely different from what the bifurcation diagram would show. It's completely misleading. If the driving is on the same order of magnitude as the dissipative time scale, so you cannot expect to see the attractors in the bifurcation diagram when you have this chaotic saddle present in the system. So that means your switch-off rate to see the quasi-periodic or quasi-stationary approach, you really have to have the switch-off rate much, much smaller than the dissipation rate. Then you can expect traversing the bifurcation diagram, otherwise not. So now, let's take our bifurcation diagram and look at another thing. So because what we also know is that we are having basins of attraction. And we already learned yesterday, so in this very simple ecological model, so where we also were changing one parameter in time, that the boundary of the basin of attraction also moves. So because this is also another set, now in the non-autonomous case, and now we would like to know what happens when we are doing this. So we are just going over bifurcations here and check what the basin boundaries are doing. So because, so they are moving, not only the attractors are moving, but the saddles move as well, and their stable manifolds also move. And these are usually the basin boundaries. And we do it with the same type of scenario, so that we have a linear increase here, and it goes from one t minus, so to say, to think about having pullback attractors. So we can change t minus, but of course, so in physics, you would start your measurement at some point, 0, and then t minus can also be 0, and then you immediately start moving your parameter, your driving amplitude, and then you go to some defined state at the very end. So here's again our bifurcation diagram, and we can go here through different intervals. And so now we have to compute the basins of attraction. So now again, we have the big problem. So because basins of attraction are not well defined in the non-autonomous case. So what do we do usually when we are looking at basins of attraction in an autonomous system? In an autonomous system, we take, so to say, again, a set of initial conditions. We integrate them forward, just straightforward, and check to which attractor they go. And then this initial condition gets a color, and this color corresponds to the attractor to which it moves. Okay? So this is what we do usually. Now we have to compute a non-autonomous basin of attraction. And the simplest idea what you can do is, of course, we take the same idea, but now, of course, we include the driving. That means we take also a bunch of initial conditions. We cover our whole state space with initial conditions. We integrate them forward, but including the driving. And then we check, so to say, at the very end, where those initial conditions went. And now we see, so to say, that first of all, these basins of attraction change, and we have a tipping of the initial conditions when we change the driving, so from one basin of attraction to another. Because you can, of course, also compute the basins of attraction at the starting point, and then see where would, in the frozen-in case, all the initial conditions would go. And then you compute it with the driving, and then you see, so to say, there are certain probabilities for parts of the basins of attraction to get into another basin of attraction. And this is what I would like to show you now. So this is what comes out, and I will restrict myself to only, not to the whole bifurcation diagram now, but we look only at the simplest case to understand what's going on. So we go from from this parameter value here to this one. This is the first interval here. And what is happening is there is a saddle node bifurcation here for a periodic orbit, and two periodic orbits appear. So that means in the beginning of the interval, so we have one periodic orbit. And so at the end of the interval, we have three periodic orbits, the green, the blue, and the red. And now we can look at the basins of attraction, how they evolve in time. And so then we compute, so to say, tipping probabilities. So that means the fractions of initial conditions which tip from one basin of attraction, because the green one is basically the basin of attraction for everyone in the very beginning of the interval, and how many will, so to say, go to the basin of attraction of the red and the blue in the course of now going over this bifurcation. So let's have a look at the basins of attraction. So they are plotted in the usual way. And so we have here now different times. So this is what I should explain maybe once again by going back here. So TR, you see, TR is this time interval, because how large this time interval is determines, because these are fixed. So the size of TR of the interval determines here the slope. So this is the rate. The TR is, so to say, now a proxy for the rate here, because the wider it is, the slower is the rate. And this is what's shown here. Now, if TR is 0, we are jumping with our parameter. So we are jumping from one parameter value to the next. So we are jumping from the beginning of the interval to the very end. And what we see is a basin of attraction like this. So the cyan ones are all the initial conditions which are still going to this green attractor here. And the blue and the red ones are the ones which end up on the two periodic solutions which have appeared in the saddle node bifurcation, which has happened when we are sweeping through this interval. But now when we see we change the rate, this would be an infinitely fast rate. Then this is a fast one, and this is a slow one. And then we see here, so that when we have a fast rate, so to say far away already from the step function, so we see that our basins of attraction become much smaller. And if it's even slower, then they become even thinner, these kind of filaments here. And if we take the rate very large, we don't see anything. So what does it mean? It means if we take now a bunch of initial conditions, we are going over a bifurcation. So even though this bifurcation happens in this interval, we would not notice it anymore. So because this bifurcation doesn't show up anymore in the basins of attraction. So that means it's basically hidden. So there was a bifurcation. If I do it very slow, there was a bifurcation and I would not even notice that. In terms of climate, this is bad news in a way. So because what we do is that we rely most of the time on time series and observations, which are coming from a network of observations, and they evolve, so to say, in time. So now when there is a bifurcation on the way, so this could mean that we would not even notice that. And this is, of course, a bad news, so that such bifurcations disappear and would not go to the newly formed attractors. And we could have basically bad surprises So when other mechanisms, so like noise-induced tipping, kicks in, so that the trajectory then jumps to another attractor, and we have not even noticed that there was one. So that this has appeared somewhere on the way, but we have not even noticed that. So that means we see here that this type of evolution of the basins of attraction leads us to another rate-dependent phenomenon, and this is basically the disappearance of the basins of attraction, and this is also then the disappearance of this type of tipping probabilities, because what is shown here is the probability for initial conditions, the fractions of initial conditions, which go either to the blue or to the red. So this should be perfectly symmetric because of the symmetry of the system. So numerically, this is not, but we see, so to say, in principle, yes. And those basins of attraction disappear, and with this, also the tipping probabilities. And so this is so how it would work. Now, to understand the mechanism, how it works, we come again back to what we already discussed yesterday. So how they can tunnel. But we do it for a simpler system because we want to understand how it works. If it's a fractal basin of attraction, then so we have a real problem. So to understand how the mechanism works, because this is nothing else than what we already touched yesterday, so that a trajectory can tunnel through the basin boundary. So there is this basin boundary crossing, and this is the whole mechanism behind the whole thing. So what we can study is, in a simplified case, two coupled bistable systems. And so this is in a driver response setup. So we have one driver, one response system. They are bistable because they are set up to have 3 solutions each. And when we couple them, they can have, depending on the parameters, so which is basically here the strength of the driving. And there could be also a timescale separation between the two, so which we just now neglect for the moment, and we will not touch upon this. And so when we change our coupling strength here, or the strength of the driver, also with a certain rate, then we go from 2 attractors in the coupled system to 4 attractors. We see that there are saddle node bifurcations in between. So we see here we are close. So these are the null-clines and the basins of attraction in the frozen-in case, what we see in the very beginning of the interval, in the very end of the interval. So we are shortly before a saddle node bifurcation when this pokes through here. So there is a saddle node bifurcation. And we go from 2 to 4 attractors in this course. When we end in the interval, we have 4 attractors, 4 basins of attraction. And we compute the relative size of the basins of attraction to see, so to say, how it changes with this driving process. So, and let's have a look how it looks like. So this is how it looks like for a fast rate and for a slow rate. We see the same initial conditions here, so which are just taken randomly from the whole bunch of initial conditions we are computing. So we see that our basins of attraction change in time, so to say, with the driver in a different way. So it depends on the rate, what we see as a non-autonomous basin of attraction. So in this case, the green is still visible, here not. So here it's already gone. So this is already gone when this rate is slow. And here it's still there. And these 2 initial conditions I would like to point out separately. So because you see, they are changing the attractor. In a fast rate, they converge here. In the slow rate, they converge here. So they have to cross the basin boundary. So this is so what we have to understand, how these trajectories really can cross the basin boundary, since in non-autonomous systems, so we know, so you cannot cross with the trajectory the basin boundary. So because these are invariant sets, so you cannot do that. And so therefore, we have to unravel this process, how you go from here to here in this case, and see, so to say, what the mechanism is in fact. Yesterday, in the example of the spruce buttworm model, we were just having a basin boundary which was 1 point. This was the saddle point. The trajectory was just passing through the saddle point. Now let's have a look how it works here. And and then we can study, so to say, why we see these changes in the basin of attraction. And now let's have a look at those two and one in the middle. So of initial conditions, this green to yellow is the boundary of the basin of attraction of the non-autonomous system. So this has nothing to do, as we see, in principle, first with what is the autonomous, in the autonomous case, the basin of attraction, because there is a saddle point here, and the basin boundary would go through this saddle point. So because it's stable manifold, let's go back here, so then we see it. So we have here is the saddle point, here is the basin boundary in the frozen in case, that's the stable manifold of this saddle point here. But the non-autonomous basin of attraction is far away from that. So because it should be here, and it's not there. So the basin boundary is here. But what is it? So what is the relationship between the basin boundary, which is in the autonomous, in the frozen in case, and the non-autonomous one? So the relationship is that the basin boundary in the non-autonomous case contains all the points which are mapped onto this stable manifold in the frozen in case. So they are all going there. So this is just before the tipping, this is just after. And so you see, this is here still green. So they are turning around at the saddle point and go to this attractor. When we are just after, so they are not turning around, they are going through the saddle point and they are reaching the other attractor. So that they go through the saddle point is the same thing. And one can look at the trajectories indeed, so to say, for the critical rate, because each trajectory, again, has a critical rate, and the critical rate is exactly that one when the trajectory gets onto the stable manifold, goes into the saddle, and stays there forever. So numerically, you never get this. So this is as close as you get. And so we see so that the trajectories, this is the saddle point. So now we see here our saddle node bifurcation. So here the trajectory goes back to the original, it's tracking, and here it's tipping to the other attractor. So these are the two, so this is for one of these initial conditions shown so that, but the critical rate would be exactly the trajectory which stays on this saddle forever. So, okay, so then we have understood how this works. And also for this system, of course, we can compute these tipping probabilities. So how much or what is the fraction of initial conditions which switches from one basin to the other? So this is, of course, depends crucially on the rate of change. And again, we see that basins of attraction disappear. So they are not there anymore. So you would not even see the bifurcation if you are very slow. And this is again due to the race between the trajectory on the one hand and the time, so the speed of the trajectory and the speed of the driver. So because when the dissipative time scale, which is the speed of which determines the speed of the attractors or the speed of the trajectory, when this is fast enough, so then the trajectory is already close to the attractor before the saddle node bifurcation happens. And then, of course, so to say, it will not notice that there is a bifurcation because it has already reached the neighborhood of the attractor. But if this is not the case, if it's too slow, so to say, then the trajectory is already in state space somewhere where it is affected by the saddle node bifurcation, and then it goes to the other attractor. And so there is a gradual decline in these basins of attractions, and some of them really disappear in this ramping process. Yeah, and this brings me to the summary. So snapshot attractors are a very nice tool to really study the dynamics of non-autonomous systems, because you get an overview what is happening, so to say, to your invariant sets in a non-autonomous setup, and you get information not only about attractors, but also about saddles, which might turn into attractors, as we have seen. And you get also information about basins of attraction, which are of equal importance. And what is always popping up again is that we have to look at these timescales. The timescales are the crucial thing, so to say, to understand the dynamics. You have the dissipative timescale, the timescale of the driver, and perhaps the timescale separation between components, as we had yesterday. So this was not the case here. But there is another timescale which might pop up if you have permanent and transient chaos. Then the escape time from the chaotic saddle is also a timescale which matters. Whether you stick for a long time on the chaotic saddle or you don't, you are hopping off quite fast. So this is also a timescale which comes into play, and all this intricate interplay is what is shaping the final dynamics. So therefore, looking at timescales is crucial for the whole analysis here. And rate-dependent phenomena are always associated with certain initial conditions. So for each initial condition, usually you get a different critical rate when the trajectory tips. So tipping is not then something which happens to all trajectories at once. So because this is really associated to each trajectory, and therefore it's also partly called a partial tipping, because only some trajectories tip at a certain rate and not all at once. Yeah, and non-autonomous basins of attraction we have seen are not identical with the autonomous ones, but so they can be understood as those initial conditions on the boundary that they are mapped with the driver onto the boundary, so which is in the frozen in case. And as a final notion, we see besides attractors, saddles are of equal importance. And this is often not taken into account. They are complicated, of course, to compute, but they are of equal importance. We have to take care of them. Thank you very much. Yeah?
Example of the saddle node bifurcation.
Yeah.
So this can also the other type of bifurcation.
Yes. So we have studied all of them, which I have shown, but different behavior. So for instance, if you go through the interval of chaotic motion, so then you get a random tipping, because tipping probabilities are then 1/2, because the chaotic motion in between mixes all initial conditions. And so therefore, even if you have at the end two attractors, then tipping probabilities are, so to say, equal 1/2. And this is completely random. So you see basically a complete mixture of the different colors, which is random. So you have a random tipping in this case. So all these bifurcations have been studied, not all of them, because so we have only taken the ones which are present in this bifurcation diagram. But in principle, you can take any and look how it looks like. Yes. But now it's not here anymore, but the relation was this one. So slower rate, so this direction is slower rate. With a slower rate, these basins disappear. So which is immediately understandable if you think about it, because when you have a slower rate of change for your driver, So then your initial conditions have more time to already converge to the attractor, because then the slow rate is slower than the dissipative timescale, and the dissipative timescale brings you to the attractor. So that means all the initial conditions would go already to the attractor where they have been in the beginning of the interval, and then you don't see anything what's happening, so to say, later on. So therefore the system does not notice the bifurcation anymore, because they are already in the attractor, all the trajectories. So why should they care that there was a bifurcation? So they don't see it anymore. So this is hidden. This is really masked when we look at this type of time-dependent basins of attraction.
Versus the rate in the optimal rate at which all the bifurcations.
Yeah, so this would be one possibility to do it, yes. So, but you have really to look at the rate, so to say, all the fractions of basins of attraction, because this critical rate is always also a different one. And it goes to 0, and so you cannot get a clear-cut bifurcation point. When you think about this here, so then we see that the size of the basin goes to 0. So, but of course, if I now would increase the resolution, since this is a phenomenon which depends crucially on the number of initial conditions. Each initial condition has another critical rate, and then therefore, so to say, it probably goes somehow, I don't know whether it's exponentially or whatever the scaling is, but it goes to 0, so to say, gradually. So we cannot nail down, numerically at least, so a threshold value. So, and this makes it different from rate-induced tipping, for instance, where you have a real clear-cut critical rate where the trajectory tips. But since it's partial tipping, so you have infinitely many initial conditions, and so therefore this is a gradual change. And this is a gradual transition as well. So there you cannot really nail down the critical rate for the whole system. So it's only the last trajectory in your resolution which tips and makes it to 0. So, but if you increase the resolution, there might be some others which are still, so to say, going to the other attractor. But finally, you end up with 0. So.
Becomes more intermittent, so that the relative probability is saturated, or
so in the case of the so what I have explained now is really where we have smooth basins of attraction. When you look at fractal basins of attraction, so you see the same phenomenon, but you see also something else. Then it depends also from other parameters how long you wait until you are at the final state, for instance. So when you measure your basin of attraction, if you do it right after, so the ramping, so you are not looking at this kind of stretch, so where you have a constant driving, so then you would see the fractal structure. Then you see really the fractal structure, because then the trajectories are still on the chaotic saddle. They have not converged anywhere. So they are just sitting on the chaotic saddle, and this immediately becomes obvious. So when you change, so to say, the time you need still to go to the attractor in the very end. So therefore, the study is quite complicated because there are too many parameters in a way. So to compute it, in principle, what I have shown now is that we start with the ramping at time 0. I could now also, of course, go backwards and change t minus. And then again, so to say, if I have a constant parameter, so for a very long time, everything would already converge to the attractor. You would not even see anything what's in the what's in the ramping. So there are always, so to say, 3 parameters you have to take into account. When do I start? How long does it take until the ramping starts? Then how fast is my ramping? And how long I wait until I plot my basin of attraction? And so these are different time scales which all play a significant role. So therefore, it's quite complicated, so to say, to make a thorough analysis, because all of those you have to change somehow to see what the impact is. If there are no further questions, then it's lunchtime. Thank you.